Hello everyone, in this video we're going to learn about the Heapify process of heaps. So if you have watched my other video about the heaps, we know that a heap is a binary tree, or can be represented as a binary tree in which the root always has a special feature. If it's a max heap, it is the maximum number or the largest item. If it's a min heap, it is the smallest item or number in the tree. So, and we'll learn about the insertion process and the delete process, or removing the root process, the root from the heap. And so when we're going to insert numbers or items in a heap one by one, we learn about that. You can watch my other video, but let's see that how we can just insert like a set of like the items in a heap. Again, for the sake of simplicity, as like my other videos, I'm using just the numeric keys here. We're assuming that data can have some numeric keys in order to do the comparison or finding the largest or smallest items. One thing that also I need to use here, or just to talk about it, is the index of the parent index of any node, which is at index I minus 1 divided by 2 is using the floor function, and I is index of the node that we're going to find its parents. So what is the or how we can actually, or where is the index I? If we show a heap using an array, so we know that each item of the array is associated with an index. So that's how we're finding the index of its parent. So let's see how the Heapify process works. Here we have a bunch of numbers, 10 to up to number to number 5, and in Heapify process, and I'm gonna first write the example using a max heap, or for the max heap. First, we're writing all the numbers which we're assuming that are stored in an array into a heap this way. So we have number 10. And then, as you remember, we are starting with the left, so it's going to be number 2 here, and then number 8. And at this step, we're not worried about the the structure of the tree to be in a heap, because we're going to fix it later. That's part of the Heapify process. So that was actually 6, and then here we have number 7, and here we have 15, and then number 5. As you see, so numbers are written in the order of like the top down and top bottom, and then left to right. So why we did define the index of the parents of any node? Because we need to find the index of the last non-leaf node. That's how or where we need to start fixing the heap structure to make it an actual max heap, or either min heap. So to find the index of the last non-leaf node, we actually need to know what is the last leaf node of the tree. Otherwise, if the index of the last non-leaf is or the like the parent of the last node of the tree is not the last node, that there should be another node that which is the last node. So as you see here, the node 1 is the last non-leaf node, which has the parent like the children 15 and 5. 4, 6, and 7, which are at the level of node 1, all of them are leaves. So the last leaf in the or the last node of the heap is this node 5 here. Okay, and as we write the indices here, let me write the indices. So 0, 1, 2, 3, 4, 5, 6, 7, and 8. So I is the, or I equal to 8. I equal to 8 is the index of the last leaf of the this heap. And to find its parent, which is the index of the last non-leaf node, we can just use I minus 1 and using the floor function. So it's going to be the floor of 8 minus 1 divided by 2, which is gonna be floor of 7 divided by 2, which is 3.5, and again is equal to 3. I just wrote it in case that you're not familiar with the floor function. So it's 3, which means that the index of the last non-leaf node is here, or the number 1 is the last, and exactly that's what we expect, and that exactly is true, as we see that 1 is the node that is the last non-leaf node. Now that we are found the index of the last non-leaf, we can see that any node before that is actually all of them are non-leaf nodes. So if you go from index 3 including to the left, these are the nodes that are like the non-leaf. So node 1, node 8, node 2, and node 10s are the ones that are like the non-leaf. So starting with the node 1 and going like to the left, we're gonna fix the problem here, because we're gonna create a max heap. So we were gonna make sure that we're putting the like the node with the maximum number as the root of that subtree. Between 1 and 5 and 15, 15 is the highest number, so we need to swap the values. So I'm going to just draw another tree, because just to keep the very first format, just to as the reference that what changes we have made. So number 15 will go here and will be swapped with 1. We're going to have number 5 here. We have 4. And then here we have 6, and then here we have 7. So we're done with number 1. So, and then after that it is 8, which is the other one here. So we're done. Check, and then 8. Between 8, 7, and 6, 8 is already the maximum number. So there's no change here, and we're also done with 8. And the next non-leaf node is 2. And between 2, 4, and 15. As you see, 15 is the largest number, so we need to swap the value. So that's going to be status of our like the tree after this swapping. So we're going to have 15 here, then here we're going to have 2, and then here we're going to have 1, here we're going to have 5, and here we have 4, and then here we have 6, and here we have 7. But we're not done yet, because as you see here, between 5, 2, and 1, 5 is the largest number, so we need just to fix that one. So here we're going to have 10, and then here we're going to have 15, here we're going to have 5, here we're going to have 1, 2, 4, here is going to be 8, and its children 6 and 7. So we're done with also the node 2. So you see that in this for this node we had a lot of changes. Actually, we had to do swapping and making sure. So the reason that we are going backward is because it's like the hierarchy of like the data, and we're going to just move up the node with the highest or the value to the very top of the tree before making decision at the very top level of the tree. So for example, here if we wanted to fix from the right to left, which means this side, which is wrong, we were we seen that 10 is already greater than 2 and 8, so we might decide that the heap is fixed. But that's not true. That's not the case. We need to fix from the very bottom of tree and go up and then just fix everything. So now we're done with 2, going to the 10, and between 10, 15, and 8, 15 is the largest number. So that's what's going to happen. 15 will be will replacing number 10. So 15, here we have 8, here we have 6, and here we have 7, here we have 5, here we have 4, that's going to be 4, and then here we have 2, and here we have 1. And as you see here, this is a max heap. Number 15, which was the maximum number, is at the very first node as the root of the tree. Number 10 is the parent of 4, 5, 2, and 1, which makes sense. And number 8 is the parent of 7 and 6, and it's already greater than these two numbers. So we're going to just also solve the same problem for for the mean heap. So we're going to just heapify these numbers that we have here and write it as a min heap. Similar to max heap, we're gonna start with writing all numbers in a top bottom left to right format. In this tree here we have 10, and here we have number 2, here we have 8, then 1, so as you see again left to right, and then we have 6, 7, 15, and 5. So we have already found the index of the last non-leaf node, which is 3, which is exactly number 1. As you see here, number 1 is the last non-leaf node. And it is a min heap, so it means that we're gonna choose the node which has the smallest number compared among the node and its two children. So between 1 and 5 and 15, 1 is already the smallest, so no change here, so we're done with the node number 1, so here. Then we're going to go again going backwards, so very similar to the max heap. The next non-leaf node is 8, and as we see here, 8 compared to 6 and 7 is not the smallest, and 6 is the smallest, so we need to do some changes. So 10 will go here, and then we're going to swap the place of 6 and 8, and the rest of the tree will be unchanged. So you might ask, how we can actually do these swapping, if we don't want to implement a tree. So for sure, because we are dealing or we can use an array to display a heap, all these things like the swapping can be done in the array. So here we swap the value of 6 and 8. So 6 is the node, is the left child of 8, so easily we can find the left child index and right child index, and then do the swapping very easily in an array, and we know that how it can be done. So here let me write 15 and 5. So I'm gonna just also write again the formula for the left child index and the right child, in case that again you want to use an array implementation to do the swapping. So the left child index, so left child is 2 times index I plus 1, and I is the index of the node that we're going to find its left child. The right child index is 2 times I plus 2. So we can just verify it for any node that we have here. Okay, after this, so we're done with the node 8 and 1 here. The next non-leaf node in this array that we had originally is the node 2, which is this one, and between 2, 4, and 1, so number 1 is the smallest one, so we need to swap number 2 and 1. So 10 here, and then we're going to have 1 as the left child, and then 2 to be the left child of that. Here we have 15, 5, the right child of 1 is 4, and no change on the right subtree, which are 6, 8, and 7. Here we don't need to do any other kind of swapping, because as you see, number 2 is already less than number 5 and 15, so we don't need to go further. After these changes, we need to go to the very last node, which is the root at 10, and between 10 and 1 and 6, 1 is the smallest, so we need to swap 1 and 10. So 10 goes here, and then we have 2, then we have 15, 5, the left child of 10 will be 4, and no change on the right subtree, gonna be 8 and 7. However, we're not done yet, because as you see here, number 10 compared to his left and right children, has a higher value, so we need to do another swapping. So if 2 is the smallest, so we need to swap the value of 2 and 10. So 2 goes here, and then 10 will sit here, and then we have 15, and it's going to be 5, and here we're going to have 4, and again no change on the right subtree of the node 1. Here again, number 10, as you see, the node 10 has a higher value compared to its right child, so we need to do one more time swapping. So it's going to be node 1, it's going to be 2, and it's going to be 6, it's going to be 8, and it's going to be 7, and it's going to be not 10 but 5 actually. So it's gonna be 5, and then it's gonna be 10, and here we're gonna have number 50. So that's the min heap version of these numbers when we use the Heapify process. The time complexity of the Heapify is big O of n, and so it might make sense to or might seem that it's actually n log n, but it is a tight band is big O of n. So at first you might look at the way that it works, the Heapify. So we have n items, and they're gonna be inserted in the tree, because we are also gonna because we are inserting all items at once. Okay, and we're gonna just do the Heapify about like the around or about like the half of the nodes, like Heapify process, and it might like take a log of n, so you might say that it's going to be n log n. But the math behind this is like complex, so I'm not going to explain that in this video. I might like just explain that in other video, that how and why exactly the Heapify process takes big O of n and not n log n. And keep it in mind, if you want to insert numbers one by one, or repeat inserting numbers one by one, the process is n log n.